covering molecules and compounds, and a compound is essentially just a combination of two or more elements. Those get broken down into two subcategories: organic and inorganic. An organic compound is essentially based around carbon, so carbon based. In an inorganic compound, there are no carbon to carbon bonds. So if in a compound, in a molecule, there is more than one, or there's more than one carbon and those carbons are connected, that makes it an organic compound. In fact, an example of an organic compound is a hydrocarbon. And a hydrocarbon is essentially all hydrogen and carbon. Hydro, hydrogen, carbon, carbon, hydrocarbons, all hydrogen and carbon. So a compound is a combination of two or more elements. A molecule is a combination of two or more atoms. So compounds are like the actual substance, and a molecule is what makes up that compound. Next, we're going to talk about something I absolutely love to talk about: biological macromolecules. All of the molecules that are like critically important to life can be broken down into four categories, and those four categories are considered our biological macromolecules. I'm going to go through those four one by one. The first one is carbohydrates. Carbohydrates are essentially made up of carbon, hydrogen, and oxygen. So hydrogen and oxygen make water, carbon, water, carbohydrates. Carbohydrates are made of carbon, hydrogen, and oxygen. They're used for energy. Most of our energy comes from carbohydrates. It is why people do not, or nutritionists do not recommend no to low carb diets unless it is like critically important, because our bodies run off of carbs. There's no way around it. And then, okay, so an example is glucose. Glucose, fructose, sucrose, lactose, they're all sugars, but they're also all carbohydrates. So carbohydrates are sugars. If you see something that ends in ose, that means it's a sugar. So if you see a really, really long word somewhere, you don't know what it means, but it ends in ose, you're like, oh, that's a carbohydrate. That's only made out of carbon, hydrogen, and oxygen. We use that for energy. Any questions about carbohydrates? Next one we're going to talk about are proteins. Proteins, let's see, are made of carbon, hydrogen, oxygen, and nitrogen. They are used for structure, support, speeding up reactions, and transport. Proteins do a lot of different jobs in our bodies. Everything from the keratin is a protein. It is what our hair, skin, and nails are made of. What makes them strong. Lactase is an enzyme that breaks down lactose. So just like you see ose sugar, it is ACE equals an enzyme. Enzymes are just specialized proteins that speed up chemical reactions. Proteins are made of amino acids. So all a protein is a big long string of amino acids twisted and crumpled and folded together to a protein. With transport, an example of a transport protein would be like hemoglobin. Hemoglobin is the protein in our blood that allows us to carry oxygen throughout all of our bodies. So proteins in general are really, really important to life. Any questions about proteins? Two more. We've got lipids and nucleic acids. Starting off with lipids, they are also made of carbon, hydrogen, and oxygen, just like carbohydrates. They don't dissolve in water. They are insoluble or hydrophobic. They do not dissolve in water. Some examples like fats, oils, and waxes. Everything from the fat that is storing energy in our bodies to the oils that are secreted out of our faces and scalps to like earwax and candle wax. Those are all lipids. They are made of carbon, hydrogen, and oxygen, and they do not dissolve in water. They are used for storage and insulation. Long-term energy storage and keeping our bodies safe. There's a special type of lipid called a phospholipid. And those are really important to cell membranes. And if we get really into cell biology, we'll go farther into what makes a phospholipid different than a regular lipid. And lastly, we have our nucleic acids. They are made of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Those are essentially the only 6 elements that biologists really care about. Every once in a while, they'll sprinkle something else in there. But carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are kind of like the backbones of biochemistry. The goal of nucleic acids is to direct protein production. We figure out which amino acids go into proteins by the order of nucleic acids, or the order of the bases in nucleic acids. The example here, DNA and RNA. DNA stands for deoxyribonucleic acid. RNA stands for ribonucleic acid. Both of them are nucleic acids. So. That is a relatively brief overview of the 4 biological macromolecules and the compounds that make them up. Anybody have any questions about that? Okay, so we're gonna kind of switch gears here for a second and go from compounds into water. What's the chemical formula for water? H2O. So a water molecule is made up of 2 hydrogens and an oxygen. So that is what a water molecule looks like, kind of like a Mickey Mouse head. Water is polar, which means we have a partial positive hydrogen and a partial negative oxygen. Oh, no. So essentially, the way atoms work is that the positive stuff is on the inside and the negative stuff is on the outside. So we've got our nucleus in the middle of this atom, and the oxygen molecule has a lot more of those positive guts inside. So all those positive guts pull all of the electrons from both the hydrogens and the oxygen down towards the oxygen. So all of the electrons are kind of, they like to hang out down here, which means we've got a partial negative over here and a partial positive up here, which essentially means that every single water molecule acts kind of like a magnet, which is how we get hydrogen bonds. Hydrogen bonds aren't like your regular ionic covalent bonds. Hydrogen bonds are kind of more like an attraction. So if we've got a little water molecule here, all of the molecules around it would kind of orient to where all of the oxygens are facing a hydrogen and the hydrogens are facing an oxygen. And those little green lines are our hydrogen bonds. These hydrogen bonds give water really special properties. Special properties like ice floating on water. In most compounds, in most substances, the solid form is more dense than the liquid form. But it's not the case with water because these hydrogen bonds kind of hold each other at arm's length. So ice forms crystals instead of just one giant solid. So there's more room between molecules of ice than there are water. So ice floats. If ice didn't float, all of the ice would like form at the bottom of a lake, and then more ice on top of that, and more ice on top of that. And organisms couldn't live at the bottom of that lake in the winter, because in the winter normally ice just freezes over the top and stuff can still live underneath. But also it would just kind of pile on one another until all of the water on Earth was frozen. It's really important the ice floats. We've also got cohesion and adhesion. Essentially, water sticks to itself and others. So when in cohesion, water sticks to itself. So that's how we get surface tension. So if you ever pour a glass of water and the water kind of bubbles up over the top, that's because those water molecules are so stuck together that they don't want to run down the side of the glass. They're going to stick together and they're going to dome up until enough pressure has been applied to like break that surface tension. With adhesion, if you ever look at a graduated cylinder, the water kind of sits in it like this. And that's because these molecules over here on the side would rather stick to the side of the cylinder instead of form like a straight line across it. So a lot of substances that don't have this surface tension quality, they'll sit in one like that. We also resist temperature change. So when, let's see. So it takes energy to make and break bonds. So when you're heating up a pot of water, like you're trying to make pasta and it's taking absolutely forever to boil this pot of water, it's because water molecules are really, really good at resisting temperature change. Because when water molecules heat up, right? Anything heating up is just the molecules speeding up. It's all just how fast the molecules are vibrating. But if we have all of these like little magnetizations, like sticking molecules together, it's really hard to get them going. You have to break those bonds in order to get them moving in order to boil them. So water is really good at resisting temperature change. It's why a lot of like industrial welding equipment has a lot of water laying around, because we only want to heat up like the part that we're welding together. We don't want that heat to like transfer and melt everything else. So like big industrial factories have a lot of water pumping through them because it's really good at holding that temperature so it doesn't heat up what we don't want it to heat up. And then we have the universal solvent. Water is really good at dissolving stuff. Not lipids. We talked about lipids being insoluble in water. But we dissolve a lot of stuff in water. I'll talk about that in a second. Speaking of solvents, we're just going to do that really quick. Speaking of solvents, we're going to talk about the difference in mixtures. So there's two types of mixtures that we're going to talk about. They are solutions and suspensions. So a suspension is essentially just a mixture that's not dissolved. A lava lamp. Really, really bad coffee with like the grounds floating around in it. If you dump a bunch of glitter in a water bottle, that is a suspension, because what is coming in it is suspended, not dissolved. In a solution, it is a dissolved but not chemically bound mixture. So if you dissolve a bunch of salt in water, it's still salt and water. It's not an entirely new substance. It's still, we got our H2O molecules and we have our NaCl. They're dissolved and equally distributed, but they're not a new mixture entirely. Solutions are made of two things: the solute and the solvent. The solute is dissolved, and the solvent does the dissolving. So, if we use our saltwater example again, right, we have our salt being our solute and our water being our solvent. It's really easy to get these two mixed up. So if you think of a really good mnemonic, let me know. A solute is dissolved and a solvent does the dissolving. There's one more aspect to water that I want to talk about. And that is when water splits. So if we've got our H2O, right, it can split up into OH minus and H plus. That little double arrow essentially is chemistry's way of saying that we are in equilibrium and we've got the same reaction happening in both directions. So just as H2O can split up into OH minus and H plus, it can come back together back into H2O. But we care about this guy. This H plus, we have a special way of measuring the concentration. That's my spell. We want to know how much H plus is in a solution, or the concentration of H plus. And that is given to us with the pH scale. When you think pH scale, what do you think? If you hear pH, what do you think? Yeah. Yeah. Mm-hmm. Yeah, exactly. Our pH scale is how we measure acids and bases. It goes on a scale from 0 to 14, with our bases up here and our acids over here. Right here, we've got our neutral 7. This is where water would be. Like we said, it was an equilibrium, so it's a neutral 7 pH. To kind of give you an example of where stuff is, sitting at about a 1, we have battery acid. And at a 13, we've got bleach. So that stuff people on TikTok have been using to dye their clothes all summer is a super basic pH. We as well as ourselves, we like to stay at a relatively neutral pH. Keeps our proteins happy. Usually we're a little bit more on the basic side, closer to an 8 than a 7, but for all intents and purposes, we are sitting at a 7. We want to maintain this. how do we keep this pH? If we're dealing with acids and bases and doing a bunch of chemistry and carrying out a bunch of chemical reactions, how are we going to maintain this neutral pH? With a buffer. Buffers essentially resist pH change without getting super specific. Let's see. Does anybody have any questions about water or our macromolecules? I could talk about macromolecules literally all day long. Anybody? Huh? Oh, I taught in AP Bio. I got one a day. Like we took an entire day for carbs, we took an entire day for lipids. And protein structure is really, really cool. Because there's just so many like complicated aspects that makes each protein different. But any questions? All right. So let's see. Let's stop this.